Okay, we are almost done. Number 5, number 6, number 7. They say, is this an identity? So we have to try and decide, is this true for every single value I can put in for x or not? So one thing is, if you want to disprove that something, if you want to say, I don't think it is, all you got to do is find one value of x for which they're both defined. So for instance, the one, if you put in x is negative 3, it is not defined over here because that makes our denominator 0. And so I can't choose x is negative 3. But I can choose any other value of x. And if I can find one where this is not true, then I have said this is not an identity. It might be conditional. There might be some value of x for which is true, but it's not true for all. So it's not an identity. So I'm thinking about how I can factor that. And let me see if I wrote this down correctly. I did not, so let me make sure. This is supposed to be a minus, so let me fix that real quick. On your sheet it's a minus, and on this it's a minus. Okie dokie. So I am thinking that it's not. So let me correct it. Now that I changed it, the one value I could not use is x is equal to 3, because that would make this undefined, division by 0. So I can't use x is 3 now. All right, so anything else? So let me try. Let me just see. I'm going to stick in 1, see what happens. X is 1. What happens when x is 1? All right, if I let x be 1, then I've got 1 squared, which is 1, plus 7 times 1, which is 7, plus 12, over 1 minus 3. All right, on this side I'll get 12, 13, I'll get 20 in the numerator. I'll get 1 plus negative 3, negative 2 in the denominator. I get negative 10 on this side. Okay. All right, when x is 1 over here, I'll get 1 minus 4. 1 plus negative 4 is negative 3. Oh, this does not equal to this, so not an identity. If I chose 1 and for some reason it worked, then I would choose another value for x and see if it still worked. So, but this one, not an identity. We are sure of that. All right, let's see. I'm going to use identities that have been established tonight for this one, just to see. I wonder if this one might be true. I don't know. Let's try it. We know that the cosine of negative x is equal to cosine of x because it's an even function. So this is cosine of x. All right. And we know that secant is 1 over the cosine of x. And we know that cosine can go into cosine one time. 1 equals to 1. Oh, I'm saying yes. I think we just proved it. Yes, this is an identity. All right, let's look here. I don't know about this one. I'm going to try to go through some things I've learned already. So what I've learned already is that the sine of negative x is also equal to negative the sine of x. And this is the cosecant of x. Okay, cosecant of x. All right. Cosecant is equal to 1 over the sine of x. So if I want to write this over 1, these will also cancel. But here I've got a negative times 1 over 1 times 1. This is equal to a negative 1. Negative 1 does not equal to 1. So I think this is not an identity. So let me just further prove this. Identity. Let me further prove this by let's pick a value for x and see if we can make it equal 1. So just like we did here, let's pick something for x. Let's pick pi. All right, so this is the original. Let me rewrite it. The sine of negative x times the cosecant of x equals to 1. I'm going to pick a value for x for which these are both defined. Oh, maybe pi is not a good one because I think it's undefined for cosecant. So let's try pi over 2. Or let's try 3 pi over 2. Let's let x equal to 3 pi over 2. That's what I'm going to try. The sine of negative 3 pi over 2 times the cosecant of 3 pi over 2. What does this equal to? What? This is 0, this is pi over 2, this is 3 pi over 2. Okay. The sine of negative 3 pi over 2 means negative 3 pi over 2 is here. It's pi over 2. And so the sine is 1. This is 1. All right. Now the cosecant is 1 over the sine of 3 pi over 2. But this is positive 3 pi over 2. Where is that? This is positive 3 pi over 2. It's here. 0, negative 1. It's negative 1. So we have 1 times 1 over negative 1 is 1 times negative 1 is negative 1. Oh, it does not equal to 1, does it? It's not identity. We further proved that by that. Okay, last two. 8 and 9 say verify the identity. So I want to show you, these may be a bit more complicated, but this is sometimes what you got to do. This is what we're given for 8. When I look at this, you might choose a different route, but I'm going to choose with the right-hand side because it looks more complicated to me. And I'm going to multiply sine x minus cosine x squared. I'm going to multiply sine x minus cosine x times sine x minus cosine x and see what happens. So that's my feeling on this one. I'm going to try there. So let me make some more room. I'm going to rewrite 8 over here. Or maybe I'll rewrite 9 over here and then I'll erase 9. Make sure I wrote it down right. 9 is the sine squared of n plus 4 times the sine of n plus 3 all over the cosine squared of n equals to 3 plus the sine of n over 1 minus the sine of n. Okay, let's do 8. And then we'll do 9. What I see here is, I'm going to begin here. I'm going to multiply this, so I'm working with the right-hand side by choice. So, what I know is that sine x minus the cosine of x times sine x minus the cosine of x over the cosine of x. Sine x times sine x is sine squared of x. Sine x times negative cosine of x is minus sine x cosine of x. Cosine times sine, negative cosine times sine is another minus sine x cosine of x. And then a negative times a negative is a positive cosine squared x. And this is all over the cosine of x. Okay. Negative sine squared, sorry. Negative sine x cosine x plus negative sine x cosine x is negative 2 sine x cosine x plus cosine squared of x all over cosine of x. Okay. Now, I'm seeing something. I see the sine x plus the cosine x, and that is the Pythagorean identity. So right here, sine x plus cosine x is the number 1, right? So this is 1 minus 2 sine x cosine x all over cosine of x. Now, at this point, I'm like, okay, what am I trying to make it look like? So this is where I look at what it's supposed to look like. It's supposed to end up looking like secant of x minus 2 sine x. And when I look at that, it kind of makes me think, oh, I see something I could do here. I can divide this denominator into each term separately. I can split this. So this could be equal to 1 over the cosine of x minus 2 sine x cosine x over the cosine of x. Well, this can divide into this, right? I can call 1 over cosine is also known as the secant of x minus 2 sine x. And now it looks like that. And we have verified that guy. Okay, last one. Hang in there. When I look at this one, what I'm going to do is work on this side right here because it looks more complicated and I see something I want to try to do. This, I want to factor this. So if factoring in trig is really whacking you out, what we can do is take out the trig. This is sine squared of n. I'm going to think of that as x squared plus 4 sine of n. I'm going to think of that as 4x plus 3. So in other words, I let x be the sine of n so that it wasn't as weird to me, okay? And if I had to factor this, I could factor this into x plus 3 times x plus 1, x squared 4x 3. That factor. So I could factor this numerator up here into x, or the sine of n plus 3 times the sine of n plus 1 over cosine squared of n. But you know what? I'm going to get this all in terms of sine because I'm looking over here and what I see is everybody's in sine. So I'm going to rewrite cosine squared into sine using the Pythagorean identity. So I know that cosine squared of n is equal to 1 minus the sine squared of n. This is equal to this. Okay, what can I do with this? Well, let me just write this in terms of x's. What if I had 1 minus x squared? This is the difference of two things being squared. This is the difference of squared. And this can be factored into 1 plus x times 1 minus x. And so I'm going to factor this right here. I'm just copy over the numerator. The sine of n plus 3, the sine of n plus 1 over 1 plus the sine of n times 1 minus the sine of n. And I notice these are the same thing. A plus b is the same thing as b plus a. So these divide into each other once. And so I'm left with the sine of n plus 3. And if I want to rearrange that into 3 plus the sine of n, that is legal, over 1 minus the sine of n. Now, why did I rearrange this one and not that one? Well, because I'm allowed to, because there's a plus and I can just flip-flop the pluses. That's okay. I'm not allowed to with the minus. I have to keep it like that. So, and I wanted it to look exactly like that. All right, that's verifying identities.